The vagus nerve is one of the most fascinating and influential components of the human nervous system. It is the 10th cranial nerve, known in Latin as nervus vagus, meaning wandering nerve, and for good reason. It originates in the brainstem, specifically the medulla oblongata, and travels downward through the neck into the thorax and abdomen, innervating a wide range of organs including the heart, lungs, liver, spleen, kidneys, and most of the digestive tract. In terms of structure, it's a mixed nerve, meaning it contains both afferent fibers, those that carry sensory information from the body to the brain, and efferent fibers, those that send motor command from the brain to the body. Approximately 80% of the vagus nerve's fibers are afferent, making it a critical sensory feedback mechanism from the body's internal milieu to the central nervous system. This single nerve is deeply embedded in the autonomic nervous system, particularly the parasympathetic branch, which governs the rest and digest state, in contrast to the sympathetic nervous system's fight or flight response. While both branches are always active to some degree, their balance determines our physiological and psychological state at any given moment. The vagus nerve helps regulate functions such as heart rate, respiratory rate, gastrointestinal peristalsis, and even the immune response via inflammatory reflexes. Because of its wide-reaching influence, modulation of vagal tone, that is, the baseline activity of the vagus nerve, is increasingly seen as a critical factor in both mental and physical health. Let's get specific with some of the mechanisms here. The vagus nerve innervates the sinoatrial node of the heart, which is the natural pacemaker. Through its efferent fibers, it releases the neurotransmitter acetylcholine onto the cardiac muscle, which slows the heart rate by increasing the time between beats. This is known as respiratory sinus arrhythmia, and it's a healthy and normal variability in heart rate that occurs with the breathing cycle. Heart rate increases slightly during inhalation and decreases during exhalation. High vagal tone is correlated with greater heart rate variability, HRV, which is a biomarker of cardiovascular health, stress resilience, and overall nervous system adaptability. Low HRV, in contrast, is associated with anxiety, depression, chronic inflammation, and poor cognitive performance. What's particularly interesting about the vagus nerve is that it is involved in bidirectional communication between the body and the brain. This is a fundamental point. It challenges the common notion that the brain dictates bodily functions unilaterally. Instead, we're learning that the state of the body, especially internal organs and viscera, sends constant updates to the brain through the vagus nerve. These updates are processed in areas like the nucleus tractus solitarius, NTS, in the brainstem, and relayed to higher-order regions like the hypothalamus, amygdala, and insular cortex. These brain areas interpret the body's physiological state and help regulate things like mood, hunger, satiety, alertness, and even perception of safety or threat. In essence, the vagus nerve acts like a surveillance and adjustment system. It detects changes in heart rate, blood pressure, gut distension, chemical signals like cytokines and hormones, and then relays this information back to the brain. The brain then sends appropriate outputs via the same vagal route or via hormonal axes, like the hypothalamic, pituitary, adrenal HPA axis. This is how you can think about the vagus nerve, not just as a passive wiring network, but as an active sensory motor loop that tunes your internal state according to both internal needs and external demands. Another fascinating aspect of the vagus nerve is its connection to the inflammatory reflex. This mechanism, first described in detail by Kevin Tracy and colleagues, illustrates how the vagus nerve helps regulate immune response. Inflammation is necessary in small, acute doses for healing and defense, but chronic inflammation is detrimental and underlies a wide variety of diseases, from cardiovascular issues to depression. The vagus nerve can inhibit the release of pro-inflammatory cytokines like tumor necrosis factor alpha TNF-alpha through what's called the cholinergic anti-inflammatory pathway. When vagal tone is high, the brain can effectively communicate with immune cells to modulate inflammatory responses, reducing the risk of tissue damage and chronic illness. This is one of the core ways that stress and emotional states, mediated by nervous system tone translate into immune dysfunction or resilience. From a developmental standpoint, the vagus nerve has a hierarchical organization. The more primitive, unmyelinated fibers, often referred to as the dorsal vagal complex, are involved in deep shutdown states such as immobilization and dissociation. These are survival responses observed in both humans and animals under extreme threat. In contrast, the more evolved myelinated fibers of the ventral vagal complex support social engagement, facial expressivity, vocalization, and states of calm alertness. This ventral vagal pathway is critical for interpersonal communication and emotional bonding. Stephen Porges' polyvagal theory builds on this and posits that our nervous system is constantly scanning for cues of safety or danger, what he terms neuroplasticity, and that our vagal response adjusts accordingly to optimize survival and social functioning. This has important implications for mental health and emotional regulation. For instance, if someone has a chronically activated sympathetic system, whether due to trauma, chronic stress, poor sleep, or poor nutrition, their vagus nerve may not be properly engaged, leading to a reduced ability to recover from stress or to enter calm, focused states. Over time, this imbalance can manifest as anxiety, depression, irritability, and poor digestion. Conversely, training the vagus nerve to engage more readily through deliberate behavioral and physiological practices can create a more flexible nervous system capable of adapting to various demands. Without getting stuck in higher arousal or shutdown states, it's also worth noting that the vagus nerve interfaces with several neurotransmitter systems. In addition to acetylcholine, it indirectly influences the release of dopamine and serotonin through its action on the gut-brain axis. Roughly 90% of the body's serotonin is produced in the gut, and the vagus nerve is one of the key channels by which information from the enteric nervous system, the second brain, is sent to the central nervous system. This highlights the importance of gut health not only for digestion, but for mood, cognition, and even motivation. A disrupted gut microbiome can interfere with vagal signaling, which may contribute to mood disorders or cognitive fog. In laboratory studies, direct electrical stimulation of the vagus nerve, called vagus nerve stimulation, VNS, has been shown to improve outcomes in treatment, persistent depression, epilepsy, and even PTSD. The FDA has approved VNS devices for these conditions. However, even without medical devices, there are behavioral tools that can effectively stimulate the vagus nerve and improve vagal tone. Techniques like slow diaphragmatic breathing, chanting or humming, cold exposure, and even positive social interaction can activate the vagus nerve and bring about changes in state. These interventions work by engaging sensory pathways that converge on the nucleus tractus solitarius and other brainstem nuclei, setting off a cascade of parasympathetic activation that translates into calmness, increased clarity, and greater emotional regulation. Let's consider the temporal dynamics of vagal activity. The effects of vagal stimulation are not always immediate. While breathing exercises may shift heart rate and vagal tone within minutes, consistent practice is necessary to induce lasting changes in the baseline tone of the vagus nerve. This is consistent with neuroplasticity principles. The nervous system changes through repetition and intensity. Over time, higher vagal tone becomes your new baseline, resulting in increased resilience to stress, improved emotional regulation, and even better cardiovascular health. Another interesting application of vagal science is in understanding the link between posture and emotional state. Because the vagus nerve is influenced by diaphragmatic movement and baroreceptor signals from the thoracic region, the way we hold our bodies can directly impact vagal output. A slumped posture may reduce diaphragmatic excursion and vagal activation, while an upright, relaxed posture may enhance it. Similarly, slow, full nasal inhalation followed by extended exhalation activates baroreceptors that increase vagal tone. This is why posture, breath, and state are so tightly linked. Finally, the vagus nerve plays a role in reward learning and neuroplasticity. When vagal activity is high during learning, especially when paired with novelty and focused attention, the likelihood of retention and synaptic change is enhanced. This is due to its modulatory influence on neuromodulators like acetylcholine and norepinephrine, which set the stage for plasticity. This has practical implications for how we can structure learning sessions, physical training, or emotional processing to optimize the brain's ability to encode and integrate new information. In summary, the vagus nerve is not merely a passive channel for autonomic signals. It is an active regulator of mood, cognition, physiology, and emotional state. It integrates sensory feedback from the body and influences key brain regions responsible for survival, adaptation, and mental wellness. Understanding and leveraging the vagus nerve gives us a profound window into how we can influence our internal state deliberately, using the body to shape the brain in real time. As research progresses, the vagus nerve will continue to emerge as one of the most potent tools for non-pharmacological interventions in neuroscience, mental health, and human performance. When we talk about mood, we're referring to an internal state composed of emotional tone, physiological arousal, cognitive appraisal, and behavioral readiness. While mood is often thought of as something that passively happens to us, the truth is that it's a dynamic and biologically malleable state, one that is deeply intertwined with our nervous system, and more specifically with our autonomic nervous system. Within that system, vagal tone emerges as a key modulator of mood through its impact on both neurochemical and physiological pathways. Vagal tone refers to the level of activity in the vagus nerve, particularly its parasympathetic branch, and how efficiently it can ramp up or down in response to internal or external stimuli. Individuals with higher vagal tone are more capable of shifting into relaxed, socially engaged, emotionally balanced states. They recover more quickly from stress, display lower levels of anxiety and depression, and show greater adaptability in the face of life's challenges. This ability to regulate internal state is not merely psychological. It is neurophysiological, and vagal tone is the instrument through which this regulation plays out. Now, let's dive into the mechanisms by which vagal tone influences mood. One of the primary ways it does this is through modulation of the hypothalamic, pituitary, adrenal axis, or HPA axis. The HPA axis governs our stress response by releasing cortisol, a glucocorticoid hormone that helps mobilize energy in the face of a perceived threat. However, chronic activation of this system, as seen in individuals with persistent stress or trauma, leads to sustained high cortisol levels, which can damage hippocampal neurons, suppress neurogenesis, and impair memory and emotional regulation. High vagal tone acts as a natural brake on the HPA axis by promoting inhibitory feedback loops at the level of the hypothalamus, effectively reducing cortisol output and buffering against chronic stress, but it doesn't stop there. Vagal tone also influences levels of key neurotransmitters that are directly linked to mood and cognition, particularly serotonin, dopamine, and GABA. For example, the vagus nerve communicates with the gut, which houses approximately 90% of the body's serotonin producing cells. Through this gut-brain axis, the vagus nerve can modulate serotonergic signaling, and in doing so, impact mood stability, emotional processing, and even sleep quality. Serotonin is not just a happiness chemical. It plays a role in inhibition of impulsivity, patience, satiety, and overall emotional regulation. Dopamine, another critical neuromodulator, is influenced indirectly through vagal activity as well. When vagal tone is increased, the balance of sympathetic and parasympathetic systems favors a calm yet alert state, one that supports goal-directed behavior, reward sensitivity, and motivation. This state is ideal for the release of dopamine in key brain regions such as the ventral tegmental area and nucleus accumbens, which are associated with feelings of pleasure, engagement, and forward movement. Without sufficient vagal tone, these systems can become dysregulated, leading to anergic states where a person feels unmotivated, disinterested, or unable to take pleasure in previously rewarding activities. GABA, the brain's primary inhibitory neurotransmitter, is also modulated by vagal inputs. When vagus nerve activity is heightened, GABAergic tone in the cortex and limbic system increases, reducing excessive excitatory activity and promoting calm, centered emotional states. This is why individuals who engage in practices that stimulate the vagus nerve, such as deep breathing, cold exposure, or vocal resonance, often report reductions in anxiety and improvements in clarity of thought. One of the most accessible and effective ways to engage the vagus nerve for mood regulation is through deliberate control of the breath. The breath is a unique physiological lever. It is both involuntary, regulated by the brainstem, and voluntary, subject to conscious control. This dual nature allows us to use breath as a portal between the conscious mind and autonomic processes. Slow, diaphragmatic breathing, particularly with extended exhalations, increases parasympathetic activity and raises vagal tone. When we breathe in, heart rate increases slightly due to withdrawal of vagal input. When we breathe out, heart rate slows as vagal influence returns. The longer the exhalation, the greater the parasympathetic activation. This phenomenon, known as respiratory sinus arrhythmia, is a real-time biomarker of vagal tone and can be measured through heart rate variability monitoring. Among the most effective breathing techniques for vagus nerve activation is the physiological sigh, a pattern that involves 2 quick inhales through the nose followed by a long exhale through the mouth. This breathing pattern, first identified in sleep research and later validated in stress regulation protocols, rapidly reduces autonomic arousal by recruiting pulmonary stretch receptors and enhancing vagal output. Just 1 or 2 cycles of physiological sighing can bring about noticeable reductions in anxiety, lower blood pressure, and shift the nervous system toward a more regulated state. But breath is not the only tool. Vocalization also plays a significant role in vagal stimulation. The vagus nerve innervates the larynx and vocal cords via the recurrent laryngeal branch. Activities such as chanting, humming, singing, and even speaking in a slow, rhythmic cadence can activate this branch, increasing parasympathetic tone and improving emotional regulation. This is not just anecdotal. Functional MRI studies have shown that humming activates brain areas associated with emotional processing and induces a shift toward relaxation. In fact, certain chants used in meditative traditions, such as Om, have been shown to synchronize neural oscillations and enhance vagal output. Another potent method for increasing vagal tone is cold exposure. The vagus nerve has afferent branches that are responsive to temperature, especially in the regions of the neck, face, and upper chest. Exposure to cold water, particularly on the face or neck, can activate the mammalian dive reflex, a primitive parasympathetic response that slows heart rate, redirects blood flow to vital organs, and boosts vagal activity. Even a simple splash of cold water or the use of a cold compress can shift your autonomic state significantly. Cold showers, cold face immersion, or deliberate cold exposure protocols can be layered with breathwork for synergistic effects on mood and state regulation. Body posture and movement also influence vagal tone. When the body is upright, with the chest open and shoulders relaxed, diaphragmatic motion is enhanced, facilitating greater vagal activation during each breath. On the contrary, slumped or closed postures restrict breathing and reduce vagal stimulation, often leading to increased sympathetic dominance. Movements such as slow yoga, tai chi, and certain forms of walking meditation leverage posture and breathing together to sustain high vagal tone and emotional balance. These practices are often underestimated in their neurophysiological impact, but offer powerful levers for emotional resilience. Social interaction and safe connection are perhaps the most powerful natural stimulants of the vagus nerve, especially its ventral branch, which supports the social engagement system. This system, rooted in the work of Stephen Porges and polyvagal theory, suggests that facial expressions, eye contact, vocal prosody, and physical proximity all contribute to the regulation of emotional state via vagal pathways. When we are in safe, attuned relationships, our nervous system mirrors and co-regulates with others. This process, called interpersonal neurobiology, is a major determinant of emotional well-being. It's why people often feel a sense of calm and groundedness in the presence of loved ones, therapists, or even pets. The interplay between vagal tone and immune function also plays a critical role in mood regulation. Chronic inflammation has been implicated in depression, anxiety, and cognitive decline. The vagus nerve, through the cholinergic anti-inflammatory pathway, can inhibit the release of pro-inflammatory cytokines and maintain immune homeostasis. This is a major discovery in psychoneuroimmunology, a field that explores how immune responses influence mood and behavior. High vagal tone reduces peripheral inflammation, which in turn can reduce symptoms of anhedonia, irritability, and mental fatigue. Another essential component to mood regulation via vagal tone is timing. The nervous system has what we call diurnal rhythms, meaning it follows a 24-hour cycle. Vagal tone is not constant throughout the day. It fluctuates in response to circadian cues, sleep quality, nutritional intake, and cognitive load. Morning sunlight exposure, for instance, helps regulate circadian rhythm and enhances the amplitude of autonomic tone across the day. Good sleep also restores vagal activity and replenishes neurotransmitter levels, while poor sleep increases sympathetic dominance and reduces our capacity to regulate mood. Timing practices like breathwork, cold exposure, or vocal toning around stress, inducing events before public speaking, after arguments, before sleep, can help preempt dysregulation and build mood resilience. What's especially encouraging about vagal tone modulation is that it's trainable. Just like building muscle or learning a language, repeated engagement of vagus activating behaviors leads to long-term changes in nervous system function. Over time, the baseline level of vagal tone increases and the threshold for entering dysregulated states rises. In practical terms, this means you become more resilient, you experience less anxiety in situations that once overwhelmed you, you bounce back faster from emotional disturbances, and you carry a general sense of groundedness into your day. Scientific studies support this. Longitudinal research on meditation practitioners, breathwork protocols, and HRV training show consistent increases in vagal tone, reductions in anxiety, and improved scores on mood assessments. These changes are measurable not just subjectively, but through biomarkers HRV, cortisol levels, inflammatory markers, and neuroimaging data. The brain literally changes as vagal tone improves, particularly in areas associated with self-regulation, such as the anterior cingulate cortex and insula. In sum, mood is not some mysterious force that overtakes us. It is the emergent property of brain-body interactions modulated by breath, behavior, environment, and thought patterns. The vagus nerve is central in this process, acting as the control dial for whether we spiral into stress and dysregulation or remain in a state of adaptive, emotionally resilient functioning. And the most empowering takeaway here is that you don't need to wait passively for mood to improve. Through targeted engagement of vagal pathways, you can change your state from the bottom up using physiology to influence psychology, breath to influence brain, and action to influence emotion. Alertness and focus are not static traits. They are dynamic physiological and psychological states that fluctuate based on internal biochemistry, environmental inputs, and behavioral habits. These states are governed to a large extent by the autonomic nervous system, the two-branch system responsible for regulating arousal, energy mobilization, and restoration. At the center of this system lies the interplay between the sympathetic and parasympathetic branches. Most people associate the sympathetic nervous system with fight or flight, and the parasympathetic system with rest and digest. While that's a helpful simplification, it's not entirely complete. In reality, both branches are active to varying degrees throughout the day. What determines our mental performance, especially when it comes to sustained attention and clear thinking, is not just how activated one branch is, but how balanced they are. The vagus nerve plays a key role in facilitating this balance. Its parasympathetic influence can suppress excessive sympathetic arousal when it is not necessary, helping maintain what we might call a calm alertness, a state that supports attention, learning, and productivity. This state is fundamentally different from high sympathetic arousal, which, while helpful for quick reactions and short bursts of action, often undermines sustained concentration by flooding the system with cortisol and norepinephrine beyond optimal levels. High levels of these chemicals can lead to distractibility, emotional reactivity, and cognitive fragmentation. Conversely, too much parasympathetic dominance, especially from the older dorsal branch of the vagus nerve, can tip the system toward hypoarousal, feelings of lethargy, low motivation, and even dissociation. This is why balance is the key. When the vagus nerve is functioning optimally, what we refer to as high vagal tone, it enables a stable baseline of physiological calm while still allowing the appropriate mobilization of sympathetic resources when needed. You can think of this like tuning a high-performance engine. You want to idle smoothly but still have the capacity for rapid acceleration when required. That smooth idle in the human nervous system is the regulated influence of a well-functioning vagus nerve. Let's explore how this plays out in terms of neurobiology. When the autonomic nervous system is balanced, when sympathetic tone is high enough to engage but not so high as to agitate, and parasympathetic tone is sufficient to stabilize, there is a favorable environment for neurotransmitters like dopamine, norepinephrine, and acetylcholine to operate in a tightly regulated fashion. These three chemicals form the neurochemical triad of focus. Dopamine, released primarily from the ventral tegmental area, is the molecule of motivation and reward prediction. Norepinephrine, produced in the locus coeruleus, acts like a spotlight on stimuli, enhancing signal to noise ratio in the brain. Acetylcholine, largely released in the basal forebrain and brainstem, enhances neuroplasticity and sharpens the signal transmission at the level of cortical neurons. Together, these molecules need to be present in a very specific cocktail for peak mental performance. Too little dopamine, and tasks feel meaningless or unmotivating. Too much norepinephrine, and attention narrows to the point of stress or paranoia. Optimal vagal tone regulates the release of these neuromodulators by influencing both central and peripheral inputs. For example, vagal afferents from the heart and lungs influence baroreceptors and pulmonary stretch receptors that send feedback to the brainstem. These signals then modulate activity in regions like the nucleus tractus solitarius and parabrachial nucleus, which communicate with the locus coeruleus and the hypothalamus. This cascade determines how much arousal the system should generate at any given time. One of the most actionable ways we can shift into a state of calm alertness is through deliberate physiological control, especially through the breath. Fast, shallow breathing sends signals to the brain that there may be a threat increasing sympathetic output. But when we breathe slowly with longer exhalations, we increase vagal tone and inhibit the sympathetic system. This doesn't make us drowsy. In fact, it primes the system for attention by reducing background noise and unnecessary reactivity. Practices like the physiological sigh, box breathing, or 4-7-8 breathing work by this principle. By increasing the length and awareness of the exhalation, they send a message to the brain that it is safe and that energy can be directed toward cognition instead of defense. There's also a time dimension to this balance. Our alertness follows a natural rhythm over the day, what's called the ultradian rhythm, consisting of 90 to 120-minute cycles during which arousal increases and then wanes. During the peak of an ultradian cycle, when we're naturally more alert, vagal tone tends to be slightly reduced while sympathetic tone increases again, not in a way that induces stress, but enough to promote focus. If we engage in behaviors that enhance vagal tone during the trough of these cycles, like a walk, breathwork, or even a short nap, we can reset the system and prepare for another bout of cognitive engagement. Sunlight also plays a role in this regulation. Light exposure, especially in the early part of the day, suppresses melatonin and enhances the release of cortisol in a controlled manner. This supports sympathetic activation for alertness, but light also affects vagal tone indirectly by synchronizing circadian rhythms through the suprachiasmatic asthmatic nucleus and its downstream targets. When our circadian rhythm is aligned, our autonomic balance is more stable, and we're more capable of shifting into alert, focused states at the right time of day. Irregular light exposure, such as using screens late at night or avoiding morning sunlight, disrupts this synchrony, leading to autonomic imbalance and reduced cognitive performance. Another way vagal tone affects focus is through its regulation of inflammation. Low-grade systemic inflammation triggered by poor sleep, diet, stress, or illness can impair cognitive function by interfering with neurotransmitter availability and synaptic plasticity. The vagus nerve helps regulate inflammation through the cholinergic anti-inflammatory pathway. When vagal tone is high, acetylcholine release inhibits the production of pro-inflammatory cytokines like interleukin-6 and TNF-alpha. This creates a biochemical environment that supports neural communication, plasticity, and sustained attention. So, even if we think of inflammation as something that happens in the body, it has very real consequences for brain function. Reducing it via vagal activation allows the brain to operate with higher clarity and efficiency. Social behavior also influences vagal regulation and alertness. Humans are social animals, and our nervous systems evolved in an environment where safety was often indicated by the presence of calm, engaged others. Eye contact, vocal intonation, and body language can all act as cues of safety, increasing ventral vagal activity. This is why social engagement in low-stress environments can make us feel more alert and connected. On the other hand, social threats such as judgment, rejection, or public scrutiny can reduce vagal tone and shift us into a sympathetic, dominant state, impairing executive function and increase rumination. Cold exposure, as mentioned previously, is another tool that can quickly shift the autonomic balance. When applied strategically, such as through brief cold showers, cold face immersion, or ice baths, cold activates the sympathetic system in a way that increases alertness without increasing anxiety. At the same time, cold also stimulates vagal afferents in the facial and cervical regions, creating a simultaneous coactivation of sympathetic and parasympathetic inputs. This dual activation helps establish a stable, alert state that enhances focus and energy. It's especially useful as a reset tool when the nervous system is fatigued or when transitioning between tasks that require different levels of cognitive engagement. Nutrition plays a subtle but important role as well. Blood sugar levels, hydration status, and micronutrient availability all influence autonomic tone and mental clarity. Spikes in blood sugar followed by crashes can destabilize the autonomic balance, leading to dips in focus. Likewise, dehydration increases cortisol levels and reduces cognitive performance. Nutrients like omega-3 fatty acids, magnesium, and B vitamin support both neurotransmitter synthesis and vagal integrity. Regular, balanced meals that include protein, healthy fats, and fiber promote stable energy and help maintain autonomic equilibrium. Cognitive control, what we think of as mental discipline, is also modulated by vagal tone. The prefrontal cortex, responsible for executive function, attention, and working memory, has dense connections with the insular cortex and brainstem nuclei that process vagal inputs. This suggests that our capacity to focus is not purely top-down, it is influenced by bottom-up signals from the body. When the body is in a state of regulated physiological calm, the prefrontal cortex is better able to inhibit distractors, maintain task rules, and execute goal-directed behavior. Conversely, when vagal tone is low, prefrontal control weakens and more primitive limbic systems take over, leading to reactive and impulsive behaviors. Training the vagus nerve to maintain optimal tone during task engagement can therefore enhance our ability to sustain attention. One of the most powerful tools here is interoceptive awareness, the ability to feel and interpret internal bodily signals. Studies show that individuals with higher interoceptive awareness have greater control over their emotional and cognitive states. Practices like body scanning, somatic tracking, and focused breathwork train the brain to become more sensitive to these internal cues, and in doing so, enhance the regulation of attention and emotion. In the context of neuroplasticity, maintaining the right level of alertness during learning is crucial. If arousal is too low, the brain doesn't prioritize the input. If it's too high, the brain perceives the experience as threatening, which reduces its openness to change. Vagal tone supports this learning sweet spot by ensuring that arousal levels stay within the optimal window of plasticity where attention is engaged but stress is low. The vagus nerve indirectly supports long-term memory consolidation and skill acquisition. This has enormous implications for how we learn, work, and grow. A calm but energized nervous system is more receptive to change. It's more plastic. Ultimately, the ability to enter and maintain alert, focused states isn't just a cognitive challenge. It's a physiological skill. And like any skill, it can be trained. By engaging in practices that support autonomic balance breathwork, cold exposure, proper sleep, nutrition, sunlight, social safety, we create the conditions for the brain to operate in its most optimal state. High vagal tone doesn't just mean being relaxed, it means being ready, being present, and being in control. Neuroplasticity is the nervous system's ability to change in response to experience. It's the foundational mechanism through which we learn new skills, form memories, reshape habits, recover from trauma, and adapt to changing circumstances. But plasticity doesn't happen by default. The brain doesn't change just because we want it to. For neuroplasticity to occur, there must be a specific set of biological conditions in place. These include heightened levels of attention, engagement, motivation, and certain neurochemicals, namely acetylcholine, norepinephrine, and dopamine, that act as neuromodulators. What we're discovering through current neuroscience is that the vagus nerve, which connects the brain to nearly every major organ in the body, is not just a passive relay in this process. It plays an active, dynamic role in setting the stage for plasticity to occur. When the vagus nerve is activated, meaning that it's effectively engaged to promote parasympathetic activity, it alters the internal environment of the brain in ways that favor learning and memory formation. One of the primary mechanisms involves the way vagal activity enhances the release of acetylcholine, a neurotransmitter crucial for selective attention and synaptic change. Acetylcholine is released by neurons in the basal, forebrain, and brainstem when the system perceives something as important or novel. These signals are stronger and more sustained when vagal tone is high. This means that activating the vagus nerve doesn't just calm the body, it primes the brain for taking in and storing new information. Another key player is norepinephrine. Unlike acetylcholine, which sharpens sensory input and enhances signal transmission at the synaptic level, norepinephrine heightens alertness and tags events as salient or meaningful. It's often thought of as a stress chemical, but in proper doses, it acts as a powerful facilitator of plasticity. The locus coeruleus, the brain's main source of norepinephrine, is tightly connected to areas that receive vagal input. When the vagus nerve is stimulated either behaviorally through breathing, cold exposure, or vocalization, or electrically through devices like vagus nerve stimulators, it increases activity in locus coeruleus, leading to a balanced release of norepinephrine that sharpens focus without tipping into anxiety. This dual modulation, acetylcholine for precision and norepinephrine for salience, is crucial for encoding new information. But the role of the vagus nerve doesn't stop there. It also influences the consolidation of memory during rest and sleep. The parasympathetic nervous system, which the vagus nerve primarily controls, dominates during deep non-REM sleep. During this phase of sleep, the brain engages in processes that replay and strengthen neural circuits formed during waking learning. If vagal tone is low, due to stress, poor breathing, or inflammation, this deep sleep is disrupted and the brain loses a critical opportunity to solidify what it learned during the day. The timing of vagal activation is also critical for plasticity. Research shows that learning followed by rest periods with high vagal tone, either through meditation, slow breathing, or a calm walk, leads to stronger retention. This suggests that you can't just load all effort during learning itself. The nervous system requires recovery windows where the parasympathetic system takes over to lock in the changes. This is a form of what's called offline processing, where the brain consolidates skills or knowledge in the absence of ongoing sensory input. High vagal tone during these periods makes consolidation more efficient, especially when paired with sufficient sleep. There's also an inflammatory component to this relationship. Learning requires synaptic flexibility, what's called synaptic potentiation or long-term potentiation LTP. Inflammatory molecules like cytokines can interfere with LTP by altering neuronal membrane potentials and blocking receptor activity. The vagus nerve, through the cholinergic anti-inflammatory pathway, regulates systemic inflammation and reduces the presence of these cytokines. By decreasing inflammation, it protects the cellular and molecular environment necessary for plasticity to occur. This is why chronic inflammation, whether due to poor diet, lack of sleep, or psychological stress, can so severely impair learning and cognitive performance. On a structural level, vagal activity is associated with increased gray matter density in brain regions involved in learning and emotion regulation, such as the prefrontal cortex, hippocampus, and insular cortex. These regions are not only responsible for encoding new information, but for regulating attention and integrating emotional valence into memories. When vagal tone is increased, these brain areas become more active and more connected to each other. Functional memory studies have shown greater coherence between the prefrontal cortex and the hippocampus in individuals with high vagal tone, suggesting more effective top-down control of memory processes and better emotional tagging of experiences. Emotional tagging is an important concept when it comes to learning and memory. The brain prioritizes information that is emotionally relevant. When the vagus nerve is active, it also modulates activity in the amygdala, the brain's emotional processing center, ensuring that emotionally significant events are more likely to be remembered. This is not just about trauma or fear. Even subtle emotional signals, like a sense of importance or personal relevance, can enhance learning through this system. By regulating how the amygdala communicates with memory centers, the vagus nerve helps determine what is kept and what is discarded from our mental library. Another powerful application of vagus nerve stimulation for plasticity is in the treatment of trauma. Traumatic memories are often stored in fragmented, disorganized ways due to the high sympathetic arousal that occurs during the event. This prevents the hippocampus from encoding the memory coherently. When vagal tone is increased, especially during therapeutic reprocessing of trauma, there is a greater likelihood that the memory can be integrated into a coherent narrative and lose its intrusive quality. This is one reason why trauma therapies that include breathwork, EMDR, or somatic practices are more effective. They incorporate vagal activation to open the window for reorganization of neural pathways. In more typical learning environments like classrooms, sports training, or skill acquisition, vagal activation can be used to extend the learning window and reduce performance anxiety. When the parasympathetic system is active, it suppresses excessive cortisol and prevents the kind of mental noise that disrupts focus. Many elite performers, athletes, musicians, public speakers use vagal stimulation techniques before performances to stay in a state of calm readiness. This is not about relaxing into drowsiness. It's about using the parasympathetic system to remove internal obstacles to performance and focus all resources on the task at hand. There's also evidence that vagal tone affects metacognition, our ability to reflect on our own thinking. Metacognitive awareness is critical for skill improvement because it allows us to evaluate our own performance, make adjustments, and strategize better. This ability is tightly linked to insular cortex function, which is influenced by vagal inputs. High vagal tone seems to enhance this self-monitoring ability, making individuals more aware of errors, more adaptive to feedback, and more likely to correct mistakes quickly. Core elements of any learning process. Interestingly, researchers have found that deliberate vagus nerve stimulation can even reopen critical periods of plasticity. These are mental windows during which the brain is especially malleable. While many of these windows close after childhood, research in animal models has shown that pairing vagus nerve stimulation with behavioral training can reopen these windows, allowing for plasticity in adulthood that would not otherwise be possible. This finding is particularly promising for fields like stroke rehabilitation, where restoring function often requires the brain to rewire around damaged areas. By stimulating the vagus nerve during movement therapy, researchers have achieved greater recovery of motor function than with therapy alone. In educational settings, the potential applications are profound. For example, teachers or learners can incorporate brief vagus-activating protocols before study sessions, such as 3 minutes of slow breathing or humming, to prepare the brain for deeper engagement. Between learning bouts, micro-recovery protocols like breath, focused pauses, or quiet walks can maintain vagal tone and prevent burnout. After learning, rest or slow movement allows for consolidation. This triphasic model, prepare, engage, recover, maps perfectly onto what we now understand about how the vagus nerve scaffolds the plastic brain. Even in digital learning environments, vagal tone plays a role. Zoom fatigue, for instance, is not just psychological. It reflects an overactivated sympathetic system due to excessive screen exposure, static posture, and lack of physiological breaks. Without the social cues and embodied behaviors that normally help regulate the nervous system, eye contact, voice modulation, movement, vagal tone can drop, leading to mental fatigue and poor retention. Incorporating physical movement, breathwork, or even music into digital learning can restore autonomic balance and optimize the environment for neuroplasticity. In all of this, one theme stands out: the body is not separate from the brain when it comes to learning. Vagal tone is the bridge. By modulating the internal state of the body, the vagus nerve sets the biological stage upon which learning and memory unfold. Whether through breath, posture, vocalization, cold, or recovery rituals, we can actively shape the brain's readiness to change. This means we can become not just better learners, but better self-directed learners, individuals who know how to prepare their own nervous system for deep work, growth, and transformation. The takeaway is clear. If you want to enhance neuroplasticity, don't just focus on what you're trying to learn. Focus on the state you're in while learning it. That state, characterized by balanced arousal, heightened attention, emotional salience, and biological readiness, is largely orchestrated by the vagus nerve. And the good news is, you have access to it right now. You can breathe differently, move differently, recover intentionally, and through these simple actions, create the internal landscape for your brain to wire itself for change.